Um, Welcome back to the deep dive. I want to start today by asking you to do something.
Okay.
It's something you've probably done 100 times, since you were a kid in elementary school.
Right.
Staring at the wall while daydreaming during a math lesson or whatever.
We've all been there.
Exactly.
Yeah.
I want you to picture a map of the world.
Huh?
Just that standard Mercator projection hanging on a classroom wall.
You know the one. It probably smells like old vinyl and dust.
Yes.
Yeah.
That exact one. Now, focus your eyes on the Atlantic Ocean. Look at the east coast of South America.
That big jutting nose of Brazil.
Sticking right out into the water.
Uh-huh.
And then you look across the pond at the west coast of Africa.
That concave curve.
Specifically around the Gulf of Guinea. Yeah.
Can you see it?
You see it. It's impossible not to see it.
I mean, it looks like a jigsaw puzzle that someone just pulled apart.
Right. And I think for most of us, that observation is just a fleeting thought. You think, that's neat.
Maybe you trace it with your finger?
Yeah. And then you just go back to your geography quiz.
Right, because it's an intuition. It's pattern recognition, which humans are very good at.
Mm-hmm.
But what happens when you take that intuition and you just refuse to let it go?
When you decide that this visual coincidence is actually the key to everything.
Exactly. The key to understanding the entire operating system of our planet.
And that is the mission for today. We are diving into a story that completely rewrote our understanding of the ground beneath our feet.
The literal ground.
The literal ground. We are moving from the old idea of what they called a fixed Earth,
A static, unmoving rock.
to the modern reality of a dynamic, churning, living planet.
And it is a journey that is going to take us from the frozen wastelands of Greenland in the early 1900s.
Down to the pitch-black depths of the ocean floor during World War II.
And finally into the really complex physics of what we now call slab pull.
It's a wild ride. And we have a hell of a protagonist for this story.
Alfred Wegener.
Wegener. Now,
He's complex. In the history of science, he is the ultimate tragic hero. I mean, he wasn't even a geologist by trade.
Which is an important part of why he was treated the way he was, right?
Oh, absolutely.
Because tragic really isn't an exaggeration here.
Yeah.
I was looking through the biographical notes for this deep dive, and the timeline is just brutal.
It is.
He's a meteorologist, primarily, an atmospheric guy. But he gets entirely obsessed with this idea of the continents moving.
He does.
He's out there in Greenland around 1912 doing his research, and he ultimately gave everything for it.
He died on the ice, November 1930.
Man.
He was on a rescue expedition, actually, to resupply his colleagues at a station called IJsmet.
Which literally means ice center.
Right. And on the return trip, his heart just gave out. He froze to death trying to prove a theory that the entire world was laughing at.
That's the really heavy part. He didn't die a celebrated genius. He didn't die knowing he was right.
Well,
He died a pariah.
he was fighting the fixed earth dogma. And today we are going to act as the jury he never got.
Love that.
We're going to look at the evidence he collected. The fossils, the rocks, the mountains. And then we're going to see how technology finally caught up to his vision.
But before we get to the rocks, I feel like we need to set the stage a bit. We need to talk about how science actually works.
Because his story isn't just about geology.
No, it's about the philosophy of knowledge.
It's about the concept of self-correction.
Right. We have this tendency, I think, to think of science as a static list of facts. The Earth is round.
Gravity pulls down.
Water is H2O. But the materials emphasize that science is actually a process.
It's a history of being wrong and then being slightly less wrong.
That's the beauty of it. Science is the only discipline that rejoices when it finds out it made a mistake.
Because that means we've found a better explanation. It's a literal mechanism for error correction.
The notes draw a comparison here that I think is really helpful for you to keep in mind as you listen to this. The shift to plate tectonics, which is what Wegener essentially started, is comparable in magnitude to the shift from geocentric to heliocentric models.
It's a total inversion of reality.
Yeah.
Think about the geocentric model for a second. 500 years ago, if you stood in a field and watched the sun rise and...
It is obvious that the Earth was the center of the universe.
Exactly. You felt stationary. The sun was moving across the sky. Your eyes told you that.
Logic dictated a fixed Earth. It was the only thing that made sense based on human census.
And in the early 20th century, logic dictated that continents were fixed. I mean, if you look out your window right now, does it feel like you're moving?
Definitely not. My coffee isn't sloshing around on the desk. The trees aren't leaning over from the wind of our movement.
So the idea that North America is cruising westward just feels absurd. It goes completely against our sensory experience.
Breaking that kind of dogma requires overwhelming evidence.
It requires you to tell everyone that their eyes and their sense of balance are actively lying to them.
There's another analogy in the research notes regarding biology, the rule of evolution. This one was actually new to me.
Oh, this is a classic example of a rule that turned out to be merely a suggestion.
Right.
Early evolutionary biologists, looking at the fossil record, thought that lineages always got larger over time.
It was called Cope's rule.
Yes. Cope's rule, you start small, you get big.
Like the horse?
The horse is the ultimate poster child for this. You have this tiny little animal, Eohippus, roughly the size of a dog.
Okay.
And over millions of years, it eventually becomes the massive Clydesdale we know today.
It seemed like a law of nature. Bigger is better for survival, right?
The gibbon.
The gibbon totally ruined the party. The research shows the gibbon lineage, which is a type of lesser ape, actually got smaller over time.
Why?
Because being smaller allowed it to be more agile in the trees, to swing faster, to evade predators.
Oh, wow.
So science had to look at that exception and say, okay, our rule is broken. We need a much more nuanced theory.
And that brings us right back to the fixed Earth dogma. Before Wegener, if you asked a top scientist at Harvard or Oxford, hey, do continents move? They would say absolutely not. They believed in the permanentism theory.
Permanentism.
The ocean basins and the continental blocks were permanent features of the globe. They might move up and down a little bit.
Like sea levels rising and falling.
Well, exactly. Isostasy. But they did not move sideways. That was considered physically impossible.
So Wegener comes along, looks at the map, and says, guys, I think they're drifting.
He called it continental drift.
And he didn't just throw it out there as a late-night hunch. This is what people always forget.
He applied the scientific method more rigorously than his critics did.
Right.
He knew he was an outsider, a meteorologist stepping into geology, so he knew his work had to be perfect.
Let's walk through those steps, because I think it's crucial to see his homework here. Step 1 is observation.
The puzzle piece fit. South America and Africa, that's the initial spark.
Step 2, the research question.
Why do they fit? Is it just a coincidence? Did the coastline erode that way by random chance? Or is there a real causal relationship?
Step 3, the hypothesis.
His hypothesis was incredibly bold. They fit because they were connected. They were once part of a larger supercontinent in the remote past that literally split apart.
And finally, the hardest part. Step 4, the prediction.
This is the make-or-break moment in science. He predicted, if I am right, and these lands were once joined, then the geology and the biology at those exact connection points should match.
It's like tearing a newspaper in half.
Exactly like that.
If I hold up 2 scraps of newspaper and the sentences read perfectly across the tear,
then they must have been one single page originally. It's the only logical explanation.
so let's go to trial.
The trial of continental drift.
I love it. Let's look at the evidence Wegener dragged out of the field. We got the coastline fit. But the notes mention a guy named Snyder Pellegrini before Wegener.
Yeah, Antonio Snyder Pellegrini. He was a geographer back in 1858. He was actually way ahead of the curve.
What did he do?
He drew maps showing the continents joined. He labeled the joined map avant, which is before in French, and the separated map après for after.
So the visual idea of them moving was floating around well before Wegener.
It was, but it was treated as a curiosity, like seeing a cloud that happens to look like a bunny.
Right.
It didn't mean there was an actual giant bunny in the sky. Wegener was the one who went past the visual map and went looking for the literal fingerprints in the rocks.
This is the part that completely blew my mind when I was reading the prep material. The rock sequences. We aren't just talking about, oh, hey, there's some granite here in Brazil and some granite over there in Africa.
No, that would be far too easy to dismiss. Granite is everywhere. Wegener looked for stratigraphy.
The specific sequence of layers.
Exactly.
I have the list right here. Let's paint this picture for you listening. Imagine you are standing on a massive cliff on the east coast of South America, maybe somewhere in Brazil. You look at the rock layers from the bottom up.
Okay, let's see the bottom layer first.
Granite, the deep basement rock, slate, then sandstone, then a layer of loess.
Which is wind-blown dust?
Right. Then siltstone, then limestone, and finally another layer of sandstone right on top.
That is a 7-layer geological cake.
Now, you get on a boat, you sail 3,000 miles across the Atlantic Ocean to Africa, you walk up to a cliff on the west coast there, and what do you see?
Granite, slate, sandstone, Logos, siltstone, limestone, sandstone.
The exact same barcode.
The probability of that sequence happening by random chance in two totally unconnected environments is effectively zero. It's statistically impossible.
Wow.
It implies that when those layers were being laid down, when that specific sand was settling, when that silt was compressing, those two places were the exact same place.
But wait, this source note's a really interesting detail here. The very top layers, the stuff above that second sandstone layer, they don't match.
And that is the smoking gun. That is exactly what the theory predicts should happen.
Explain that, because it seems counterintuitive at first.
Well, the basic rule of geology is superposition. Old stuff is on the bottom, new stuff is on the top.
Makes sense.
The continents split apart roughly 80 to 100 million years ago. So the rocks formed before the split. The bottom layers of our cake are identical because they were formed in the same environment.
Right.
But the rocks formed after the split, the top layers, are completely different.
Because by then, South America was moving west and Africa was staying put.
Exactly. They were in different climates, different environments, experiencing totally different erosion patterns. So the rock record diverges at the exact moment of the split.
That is incredibly cool. The rocks literally tell the story of the divorce.
They do, but if the rocks are the divorce papers, the fossils are the custody battle.
Okay, let's talk about the critters. This is where biology firmly backs up geology.
Wegener's realized that if the continents were joined, animals would have just walked freely between them.
Sure.
But if they were always separated by a giant ocean, you'd have totally different species evolving in total isolation.
And he found the exact same species on both sides.
Hmm.
But the critics argued, hey, maybe they swam. Maybe they walked on ice bridges. Maybe they floated on logs.
That's always the counter-argument from the permanentists. Rafting. They pictured these animals clinging to driftwood after a huge storm and just floating 3,000 miles across the Atlantic.
Which sounds ridiculous.
It is. And Wegener picked his witnesses very carefully to disprove it. He didn't pick birds, obviously. He didn't pick fish. Take Mesosaurus.
The freshwater reptile.
This is key. Mesosaurus was a small, lizard-like reptile. It lived in freshwater lakes and rivers. It was absolutely not a marine animal.
So it couldn't handle the ocean.
Its physiology couldn't handle saltwater osmosis. If you put a Mesosaurus in the middle of the saltwater Atlantic Ocean, it dies. Immediately.
It can't swim 3,000 miles.
It can't swim 10 miles in salt water, yet we find Mesosaurus fossils in a very specific band in South America and a matching band in Africa. Nowhere else in the entire world.
So unless Mesosaurus built a boat...
The land was connected. It lived in a single large freshwater system that spanned what is now both continents.
That's undeniable.
And then you have Glossopteris.
The plant.
It's a fern with these big, tongue-shaped leaves, but crucially, it has very heavy seeds.
So they don't blow away.
They aren't the kind of seeds that blow in the wind for thousands of miles, and they definitely don't float well in seawater. Yet, fossils of this fern are found in South America, Africa, India, Antarctica, and Australia.
Wait, Antarctica?
Yes. Which also tells us that Antarctica wasn't always frozen solid. It was part of this lush, green supercontinent. It literally had ferns growing on it.
That brings up a great point about climate from the notes. Wegener found evidence of glaciers in places that are now tropical.
Right. This was another huge nail in the coffin for the fixed Earth. He found glacial striations, these deep scratches in the bedrock caused by moving ice sheets, in India and Africa.
Places that are baking hot near the equator today.
So you only have two options. Either the equator used to be covered in a massive ice sheet.
Which would mean the whole world was a giant snowball, which we know wasn't true from other evidence.
Exactly. Or option two. Those landmasses used to be situated near the South Pole.
Wow. So India was sitting near Antarctica.
Yes. It has since sprinted north across the globe and crashed into Asia.
It's just piling up. You have the map fit, you have the rock barcode, you have the freshwater reptile, you have the fern, and finally you have the mountains.
The structural evidence, this is for the people who really need to see the big picture on a macro scale.
Right. So if you look at the Appalachian Mountains here in the U.S., running right down the East Coast, and you look at the geology, the specific rock types, the complex folding patterns, and then you go across to Morocco and look at the Atlas Mountains.
They are the exact same mountain range.
That just breaks my brain a little bit. The Appalachians and the Atlas Mountains are siblings.
They are twins separated at birth. And it goes north, too. The mountains of Ireland, the Scottish Highlands, and the Skanses in Scandinavia. If you theoretically close the Atlantic Ocean back up, all those mountain chains link up into one single continuous belt.
It's like a broken necklace.
That is the perfect analogy. They were formed by the same massive collision event when the continents came together to form the supercontinent, and then they were violently torn apart when it broke up.
Okay. So Wegener collects all of this data. He writes his book, The Origin of the Continents and Oceans, and publishes it in 1912. He drops this massive binder of evidence on the desk of the Geological Society. He's probably thinking, I've done it. I've solved the Earth.
Right.
And the scientific community says
Out.
they just rejected it, flat out.
They didn't just reject it, they actively ridiculed him. They called it German pseudoscience. They said he was a mere meteorologist who should stay in his lane.
Good grief.
One prominent scientist literally called it the footloose wanderings of a deluded mind.
That is incredibly harsh.
Yeah.
Why? How could they look at the Mesosaurus and the rock layers and just say no? Were they blind?
No, they weren't blind. They were physicists. And this is where we really have to be fair to the critics because it's an important lesson in science.
Okay, I'm listening.
It wasn't that they denied the evidence existed. They saw the fossils. They couldn't explain them, but they didn't deny them. The main problem was that Wegener had a fatal flaw in his theory.
The mechanism.
Exactly. He had the what, but he didn't have the how.
He couldn't explain what force was actually strong enough to push an entire continent.
Right. Think about the physics of it. At the time, geologists believed the ocean floor was this thick, solid, completely immovable rock.
Sure.
Wegener was suggesting that the continents were somehow plowing through that solid rock like a snowplow pushing through thick ice.
And the math on that just doesn't work.
It doesn't work at all. If a continent tried to plow through the solid ocean floor, the continent itself would crumble. The friction would be way too high. The granite of the continent would shatter long before the basalt of the ocean floor gave way.
Did Wegener even try to offer a mechanism?
He tried. He grasped at straws. He suggested things like centrifugal force from the Earth's rotation spinning them outward, or tidal forces from the moon pulling them along.
And the physicists crunched the numbers on that.
They did. They calculated the required force and said, Wegener, look at the chalkboard. The pulling force from the moon is 1 billion times too weak to move a continent. And if the tidal force was somehow strong enough to move a continent, the friction would also stop the Earth's rotation in about a year.
Ouch. So he was right for the wrong reasons.
He was entirely right about the result, the movement, but totally wrong about the process. And in science, if you don't have a mechanism, you don't have a theory.
You just have a curiosity.
You have a pile of unexplained anomalies.
So the theory essentially goes into hibernation. Wegener dies in 1930, freezing on the ice, thinking he totally failed.
It's really tragic. He died thinking his life's work was treated as a joke.
Before we move to the resurrection of the theory, let's visualize what he was proposing. He called his supercontinent Pangea.
Which is Greek for all lands.
And the timeline of the breakup is fascinating to visualize for you listening at home.
It really is. We start the clock about 225 to 200 million years ago. That's when the breakup begins. This is during the Triassic period.
Then we jump forward to about 135 million years ago. What does it look like?
By then, Pangea has split into 2 massive chunks. You have Gondwana in the south, that's Africa, South America, Antarctica, Australia, and India.
Okay.
And then Laurasia in the north, which is North America, Europe, and Asia.
And then 65 million years ago.
That's when the Atlantic really unzips. South America and Africa finally separate, and eventually, over tens of millions of years, we get the map we see today.
But the story doesn't end with Wegener's death. We have to fast forward. And oddly enough, the thing that saves this geological theory is the most destructive event in human history.
World War II.
World War II.
War drives technology. It always has. And in this specific case, the technology was sonar.
Submarine warfare.
Exactly. If you're a submarine commander in the Atlantic, you are practically flying blind. You desperately need to know how deep the water is so you don't crash into a mountain.
Right.
You need to know where the enemy subs can hide. You need to know the acoustic properties of the water layers. So the Navy started mapping the ocean floor with high-resolution sonar.
Before this, what did we actually think the bottom of the ocean looked like?
We thought it was just a flat, boring, muddy plain.
Really?
Yeah, like the bottom of a stagnant pond. Just an accumulation of dead sediment piling up for billions of years. We thought it was the oldest, most boring place on Earth.
But when they turned on the sonar...
They were absolutely shocked. The ocean floor isn't flat. It is a landscape as dramatic, if not way more dramatic, than anything we have on dry land.
They found massive underwater mountain ranges. Deep, terrifying trenches that go down 7 miles into the dark.
And crucially, they mapped the mid-ocean ridges.
This is the massive turning point for the theory. the mid-ocean ridge.
Imagine a massive mountain range running right down the center of the Atlantic Ocean, perfectly mirroring the coastlines of the continents.
It winds around the globe like the seam on a baseball.
It is the longest mountain range in the world, and it's almost entirely underwater.
This directly leads to the revival of the theory in the 1950s and 60s. A guy named Harry Hess and the concept of seafloor spreading.
This was the missing piece Wegener needed. Hess was a Navy commander and a geologist. He looked at these sonar maps and realized the ocean floor isn't a passive, solid surface that continents plow through.
Okay.
The ocean floor is active, it's constantly being created.
Created, like from scratch.
Yes. At the mid-ocean ridge, hot magma rises up from the mantle, it erupts, it cools down in the water, and it forms brand new crust. And that new crust physically pushes the old crust aside to make room.
So it's not a plow pushing through ice. It's a conveyor belt.
In a sense, yes. The continents aren't moving through the ocean crust. They are riding along with it as it spreads outward from the ridge. They are just sitting on the conveyor belt.
This explains the crazy age difference we see, right?
Mm-hmm.
The notes make a really big point about young versus old rock.
This was the final piece of data that nailed the coffin shut on the fixed Earth idea. When we finally started drilling into the deep ocean floor and taking core samples, we found that the rocks down there are shockingly young.
How young are we talking?
Geologically speaking, they are absolute babies. The oldest ocean floor on the entire planet is maybe 200 million years old.
And the continents.
Billions of years old.
Yeah.
We have rocks sitting on continents right now that are 3 or even 4 billion years old.
Wait, so the ocean floor is constantly being recycled, but the continents are these ancient permanent rafts just floating on top.
Exactly. Continental crust is mostly made of granite. It's lighter, it floats high. Oceanic crust is made of basalt. It's heavy, it's dense, and it's totally temporary. The ocean floor is born at the ridge, it moves across the planet like a belt, and it dies by sinking into a trench. The continent just rides the wave above it.
You can actually see this ridge in action, right? The source mentions Iceland.
Oh, Iceland is arguably the coolest place on Earth for a geologist. It's one of the very few places where the Mid-Atlantic Ridge actually rises above sea level.
Whoa.
There is a specific rift valley there called Thingvellir, where you can literally stand with one foot on the North American tectonic plate and your other foot on the Eurasian plate.
And they are actively moving apart while you stand there.
Yes, at about 2 centimeters a year, the Earth is literally tearing itself open right between your boots. If you stand there long enough, millions of years, you'll do the splits.
Okay, so now we have the evidence from Wegener. We have the motion from seafloor spreading. We know that it happens.
Yes.
But we still need to nail down the exact mechanism, the actual physics.
Yeah.
Because for a long time, even when I was in school, we were taught that it was just convection, like soup boiling in a pot on the stove.
Right, the convection cell model. The idea that the mantle is boiling underneath and the plates are just passive scum floating on top of the soup. The swirling currents just drag them along.
But the source material for this deep dive gets really specific here. It says that model is actually outdated.
It is. Modern geophysics has moved on from that. We now know that the plates aren't just passive passengers on a current. They are the active drivers of the movement.
This is where we get to slab pull.
Slab pull is the absolute gold standard today. The materials reference a landmark study by Forsyth and Ueda from 1975.
1975. So this is fairly recent in the grand scheme of scientific history.
Very recent. They used something called inverse theory to analyze the tectonic forces. Basically, they looked at exactly how fast all the different plates were moving and worked backward mathematically to figure out what specific forces were pushing or pulling them.
So they asked, are the plates attached to big convection currents, the ones moving fast? Or are the plates attached to subduction zones moving fast?
Exactly. And they looked closely at 2 main competing forces, ridge push and slab pull.
Okay, what is ridge push?
Ridge push is that magma coming up the ridge we just talked about. Gravity pushes the new, high-elevated ridge down and outward. It physically pushes the plates apart. For a long time, we thought that push was the main engine driving everything.
But the math says?
The math says it contributes maybe 5 to 10% of the total force. It's incredibly weak. It's just a gentle nudge.
So what's driving the other 90% of the movement?
Slab pull.
Okay, we need to really unpack slab pull. This is the core physics of the episode. Imagine I'm, say, 5 years old, or maybe a really smart 12-year-old. How does this work?
Okay, let's try a visual. Imagine a thick towel floating on top of a bath full of water. It just sits there.
Makes sense.
Now imagine you attach a heavy lead weight to one edge of that floating towel.
The edge with the weight sinks down into the water.
And as it sinks, what does it do to the rest of the towel?
It drags the whole towel across the surface of the water.
Exactly. That is slab pull. The towel is the oceanic plate. As it moves away from that warm volcanic ridge where it was born, it starts to cool down.
And rock contracts when it cools.
It contracts and it gets significantly denser, much heavier.
So it becomes an anchor.
Yes. Eventually, it hits a deep trench, which we call a subduction zone, and it starts to sink down into the deep mantle. Once that heavy, freezing cold tip starts falling into the earth, gravity takes over entirely. It pulls the rest of the massive plate from behind it.
So the plate isn't being pushed from the back at the ridge, it's being pulled from the front at the trench.
It's falling off the edge of the table and dragging the entire tablecloth with it.
That makes so much sense. And looking at the map, this explains perfectly why the Pacific Plate is moving so fast.
The Pacific Plate is completely surrounded by deep trenches, the famous Ring of Fire. It has massive heavy anchors pulling it in almost every single direction simultaneously, so it moves incredibly fast, up to 10 centimeters a year.
Compare that to the Atlantic Ocean.
The Atlantic has almost no subduction zones at all, no anchors. The North American plate is barely being pulled by anything. It's mostly just being gently nudged by that weak ridge push, so it moves much, much slower, maybe 2 centimeters a year.
Now, there's a rather scary-looking formula in the notes here, but I want to tackle it because I think it proves to you that we aren't just guessing about this anymore. The formula is F sub p equals K times delta rho times L times the square root of A.
I know it looks like alphabet soup, but don't panic. It's actually quite elegant when you break it down. It's literally just a recipe for how strong the Earth engine is.
Let's translate it. F sub p is the slab pull force. That's our result.
Right. And that force equals K, which is basically just gravity. The gravitational constant, 4.2 G in this context.
Gravity, check. That's pulling it down.
Times delta rho, that's the density difference. This is the absolute crucial number. It's about 80 kilograms per cubic meter.
Meaning?
That is how much heavier the cold sinking slab is compared to the hot, gooey mantle it's sinking into.
So if there's no density difference, there's zero sinking.
Correct. If the slab was the exact same weight as the mantle beneath it, it would just float there forever. It desperately needs to be heavy and cold to sink.
Then we multiply times L, which is the length of the slab dangling down.
A longer slab means more total weight, which means more pull. Just like a long metal chain hanging off the edge of a table pulls much harder than a short one.
And the last variable, the square root of A.
A stands for age.
Why does the age of the rock matter to how fast it moves?
Because age directly equals temperature. The older the rock is, the longer it has had to sit out there and cool down away from the ridge.
Oh, right.
And the colder it is, the denser it is. So a really old 100-million-year-old slab pulls much, much harder than a young, warm 10-million-year-old slab.
That is fascinating. The entire engine of the Earth depends heavily on the sheer age of the rock.
It absolutely does. A young slab is warm and buoyant. It actively resists sinking. An old slab is freezing cold and heavy. It desperately wants to sink.
And understanding this math clears up a huge, huge misconception about the asthenosphere.
Yes, it does. So the asthenosphere is the upper layer of the mantle right below the plates. It's this gooey, semi-molten rock layer. For decades, textbooks taught that the asthenosphere was actively flowing like a river and dragging the plates along with it.
Like a river carrying a wooden boat.
Exactly. But the slab pull model totally proves that's backwards. The asthenosphere is actually resisting the plate's movement. It's thick. It's highly viscous. It's dragging against the bottom of the plate.
So the plate is moving despite the friction, simply because that heavy anchor is pulling so hard.
The luggage is basically moving itself.
That is incredible. The convection we see in the mantle is a result of the plates moving, not the cause of it.
Exactly. The sinking plate stirs the mantle, not the other way around.
This really brings us to what we call the unified theory. We know it as plate tectonics, and the notes say it's considered the grand unified theory of Earth sciences.
It truly is. In biology, the grand unifying theory is evolution by natural selection. In physics, it's quantum mechanics and general relativity. In geology, without a doubt, it is plate tectonics.
Because it connects everything.
Tectonics comes from the Greek root word meaning to build. It literally explains how the entire surface of the Earth is built. Before this theory came along, paleontology, which is the study of fossils, and seismology, the study of earthquakes, were totally separate academic fields.
They didn't talk to each other.
They had no reason to, but now
Now they're intimately part of the exact same story.
You cannot fully understand why a dinosaur fossil is in Utah without understanding the rifting of the Atlantic Ocean. You cannot understand why a tsunami hits Japan without understanding the subduction of the Pacific Plate. Plate tectonics links the three great planetary cycles.
Char, let's hit those cycles briefly for the listener.
You have the hydrologic cycle, the rock cycle, and the tectonic cycle.
Oh.
The tectonic cycle drives the rock cycle. It takes rock, melts it down, and spits it back out as brand new igneous rock at the ridges.
Then the hydrologic cycle takes over.
Right. Water, rain, and weather physically erode that new rock down into sedimentary rock.
And then subduction takes that sedimentary rock and cooks it under immense pressure into metamorphic rock.
It is a giant, continuous planetary recycling machine. If the tectonic plates ever stopped moving, the Earth would eventually just erode completely flat, and complex life would probably die out.
Wow. And this massive recycling machine creates the different types of plate boundaries we always hear about on the news. We've mentioned divergent boundaries already. That's the mid-ocean ridge moving apart.
Creating brand new land. That's the global construction zone.
Then we have convergent boundaries.
That's the demolition zone. Subduction. Plates crashing head-on. One heavy plate going deep under the other lighter one. This is exactly where you get the biggest, most devastating earthquakes and the most explosive volcanoes.
The Ring of Fire in the Pacific.
Exactly.
And the notes mention something incredible here. These subducting slabs actually cool the interior of the Earth.
They really do. These freezing cold slabs of ocean floor sink all the way down into the mantle. Some of them even reach all the way down to the core mantle boundary deep inside the planet.
And they act like ice cubes.
They literally refrigerate the deep interior of the planet. And that cooling differential actually helps to drive the massive convection of the liquid outer core, which, crucially, is what creates our planetary magnetic field.
Wait, really? So without subduction, we might not even have a magnetic field to protect us from deadly solar radiation.
It's a very real possibility. Plate tectonics essentially keeps the planetary shield up.
That is mind-blowing. Okay, and finally, the third type, transform boundaries.
This is where plates aren't colliding or separating, but just sliding right past each other laterally.
The San Andreas Fault in California.
Everyone knows the name, but here's a specific detail I absolutely love. The San Andreas isn't just a crack in the ground running through California. It is the literal boundary line between the entire Pacific Plate and the North American Plate.
So Los Angeles is physically on the Pacific Plate.
Yes. LA is riding the Pacific Plate, moving northwest, heading towards San Francisco. San Francisco, however, is firmly planted on the North American Plate.
Oh, man. So eventually, millions of years from now, LA will literally be a suburb of San Francisco.
It's a traffic nightmare waiting to happen, and that lateral grinding motion is exactly why the earthquakes in California are so shallow and so incredibly destructive. They aren't deep subduction zone quakes miles underground. They are surface tears right where people live.
We've covered the really big picture here, but I want to geek out on a few very specific anomalies and details from the source material before we wrap this up. There are some moments in here that I think you will absolutely love.
Let's do it. Hit me.
First up, the true edge of the continent.
Oh, this totally changes how you look at a map forever. We all inherently tend to think that the continent ends at the beach, where the water hits the sand.
It seems perfectly logical. Land ends, water begins.
But that's purely just where the water level happens to be right now in this exact climatic moment. If you lowered the global sea level by, say, 100 meters, the beach would move miles and miles out.
So where is the actual geological edge of the continent?
It's the continental shelf. If you swim out from the beach, the bottom of the ocean slopes very gently for quite a while. That entire sloping area is still continental crust. You are physically still standing on the raft.
Okay.
Then suddenly, there is a massive, steep drop-off. The continental slope, that sheer drop-off, is the true structural edge of the continent.
So the beach is a lie.
The beach is entirely temporary. The shelf is the permanent structure. The actual continents are significantly bigger than they look on a standard map, simply because the edges are currently flooded by seawater.
That is so cool. Another detail here, the Pacific Plate. I always just assumed tectonic plates were named after the continents they carried. Like the North American Plate carries North America, the African Plate carries Africa. But the Pacific Plate,
It's completely unique. Almost the entirety of the Pacific Plate has no continental landmass on it at all. It's almost 100% oceanic crust. It's just one giant, fast-moving slab of heavy basalt.
and then there's the ghost story in the notes. The Farallon Plate.
The lost tectonic plate.
It sounds like Atlantis or something.
It sounds mythological, but it's hard science. There used to be a massive, huge plate sitting right between the Pacific Plate and the North American Plate. It was called the Farallon Plate.
If it was so massive, where is it now?
It's under us.
Under us, like right beneath our
And
feet.
it got subducted. North America literally ran it over. As the North American continent was being pushed westward, because the Atlantic Ocean was opening up and pushing it from the east, it acted like a bulldozer and entirely consumed the Farallon Plate. The whole plate just went down under the continent.
Did a whole plate disappearing leave a mark?
A huge one. As that massive slab of rock went underneath, the friction and displacement pushed up the land directly above it.
No way. It created the Rocky Mountains.
Yes. The severe and Laramide orogenies, which are the geological terms for those specific mountain-building events, were directly caused by the ghost of the Farallon Plate scraping and pushing up from deep below.
So the Rocky Mountains are essentially a tombstone for a dead tectonic plate.
In a very real way, yes. And there are actually tiny pieces of it still left on the surface. The Juan de Fuca Plate, right off the coast of Washington State, and the Cocos Plate off the coast of Mexico, those are the very last surviving scraps of the mighty Farallon. The entire rest of it is buried deep in the Earth's mantle.
That is just wild. It really reinforces the idea that the map hanging on the wall is not permanent at all.
Yeah.
It's just a single frozen snapshot of a movie that's been continuously running for 4.5 billion years.
And we are only getting to watch one single frame of it.
This has been an incredible journey today. We started with poor Alfred Wegener freezing to death in Greenland, just looking at a map and stubbornly saying, this fits together.
We went through the harsh rejection, the total lack of a physical mechanism.
Then the war, the submarines, the sonar, the totally accidental discovery of the mid-ocean ridges.
And finally, the complex, elegant math of slab pull.
It's essentially the story of how human beings finally learned to listen to the planet.
And it explains the fundamental why of our world. Why the majestic mountains are exactly where they are. Why the ground suddenly shakes and destroys cities. Why we can find tropical ferns buried under the ice in Antarctica.
It truly is the operating system. If you don't understand plate tectonics, you just don't understand the Earth.
Period.
I want to leave everyone listening with a final thought today. Looking back at that core idea we discussed earlier of science being a self-correcting process.
It's arguably the most important takeaway from this entire story.
Think about it. The fixed Earth view was entirely logical to them. It made perfect sense to their senses. But it was completely wrong.
Wegener's continental drift view was radical. He was completely right about the movement happening, but he was dead wrong about the physical cause.
And now, our modern, highly advanced view of slab pull continues to refine the complex math every single year.
We are always refining. We are always correcting our mistakes.
So the provocative question I have for you, and for everyone listening, is this. What scientific belief do we hold today, right now, that seems totally logical, totally solid, just like the fixed Earth did, that might be completely overturned tomorrow as new technology reveals new evidence?
That is the exact question that keeps scientists awake at night. And honestly, it's the exact reason we keep exploring.
Keeps me awake, too. Thanks so much for joining us on this deep dive. Keep looking at the map, keep asking questions, and we'll see you next time.